Hello, I'm David. It's semester 2, 2023, and this is the revision seminar for data analytics. Yeah, we'll figure out what we're going to talk about in just a minute. I also need to say I'm not part of the people who run this course. I'm from the Maths Learning Centre. It's our job to help everyone in the whole university engage with maths when it appears. Your course has the word data in the title, so obviously maths has appeared in this course. And that's my job. And one of the things we do is revision seminars before the end of, as we get closer to the exams. I just want to check something. When's your exam? Poor things. And you just handed in your last assignment yesterday, right? Nothing like cutting it fine. And what kind of exam have you got? Have you got is there multiple choice questions? It's all multiple choice? Sometimes that's better, sometimes that's worse. And have you been given any sort of indication, like a practice exam or anything like that? Okay, good. My recommendation is always to look at the stuff that the people who run the course have given you. That's your best call. But I will also say, as a general piece of exam advice, the practice exam is not a description of all the things that will be in your exam. It's a little more like trying to go on a game show like The Chaser. And so if you watch today's episode, you'll know generally how the show works, but you will not be able to study today's questions and be able to use those same answers tomorrow. So it's the same thing with exams. It's a general idea of the hardness and the kinds of questions you're going to be asked, but it doesn't cover everything that might be in the exam. So just wanted to point it out. And so it's not just, I'm sure your lecturer has told you about this, but it's not just him. Just wanted to repeat the story. Okay, so what have we got? Just going to check it's actually recording. No, it is good. So I've got stigmatization, how to do it on a calculator or other most efficient way for the exam. When to reject a hypothesis of what it means to reject one. Sounds counterintuitive. Yes, it does. Whoever wrote that, that is 100% true that the hypothesis testing feels counterintuitive. Estimation hypothesis testing, two populations. Best chart to use. Probability calculations in general. And then we've got a second one for hypothesis testing and P and T from the people on Zoom. Okay, well, we've got several votes for this estimation, hypothesis, etc. stuff, so we might have a look at those. But I will have a quick look at this some notation as well. And I'm just going to pause the recording. Please remind me to turn it back on again if I forget later when I next start talking. But I want to have a quick look inside your My Uni. Is that a fear you have? Was there something like that in the practice exam? Haven't looked at it. Well, it's probably a good idea not to look at it too early. Was it something that you were asked in like weekly quizzes or anything to just straight up calculate them with a list of numbers? Okay. All right. So I just want to point out this notation that thing there, that's the standard deviation of a sample. Pretty sure. The n-1 is there because of some very fancy probability theory that tells you that if you divide it by n, it comes out to be slightly off the answer that you were hoping for on average. So The question was, just for those who didn't hear it, was there a situation where you have to determine whether it's a sample or population standard deviation? I can't tell you that. But almost always, if you've been given a list of data with no probabilities to go with them, it's a sample standard deviation. Yeah. Correct. So with the population, you have a list of numbers and a list of probabilities to go with them. Just a second. You have like 1.3, 2.8. Something like that. That's a population distribution table, and the standard deviation would be figured out by going this times. You'd have to find the mean, and then you'd have to take off the mean of everything and square them and then multiply them all by the matching probabilities. Do you want me to show that thing as well? Okay, cool. I'll do both of those. Okay. So this is a sample. And in a sample, what you'd get is you just have a list of numbers. You just have a list of numbers. There wouldn't be any probabilities to go with them. It's possible that some of the numbers will be there twice. It's just a list. And that's what a sample looks like. But if there's probabilities to go with them, then it's about populations. Because in the samples, we don't really know the probability. All we have is the numbers we collected today. So it's almost always true if they just give you a random list of numbers, then they're looking for a sample standard deviation. But I can't guarantee that. The words that go with it will help. So the reason they would have a formula to have with an N here is because if you were told that these were the only numbers that there were and they all were equally likely, that would be the same as giving you a table of probabilities because they told you they were equally likely. So just read the context of the question and decide whether a sample has been taken. And so they might say, we had a survey and these were the scores, these were the average of the 5 scores for teaching excellence in the SELT survey for each person. You go, okay, that's just one group of people. Or this was the reaction time of 6 people to clicking on the link in an ad. Well, 6, 1, 2, 3, 4, 5, 6, 7, 8 people clicking in an ad. They'll always give you a context. Now, if they don't, this is the only way to decide. List the numbers plain, do a sample. Probabilities, do a population. That's what I would suggest. So would you like me to show you doing both of these calculations? Okay, let's go. I wonder if I can make that light less extreme. One moment. You'll see it. Okay, cool. It's just now not the annoying multiple shadows. We're all in mood lighting now. And you can still see that okay? What about you online? You can still see that okay? Stick up your thumb if you... Oh, that's good. Yeah, cool. We'll just make sure we put that back on. Okay. Because I turned off the sharing and turned it back on again. Well, let's have a look. I'm just going to copy them onto this page. So if you read the notes later, you don't have to flick back and forth. And so that I don't have to flick back and forth. The sample of reaction times in seconds is this. What is the sample standard deviation? Okay. So the formula is this, and this is short for, so when you read math notation, you always go to the middle. So the square root is the last thing to happen because all of this is under the square root. The divide by n minus 1 is the second last thing because everything's on the top of that fraction. And then the sum is second last, and then the squared is, yep, and then this thing is the first thing to happen. And so what this is saying is that for every I, and I stands for whichever individual I'm up to, I have to take the x, the value that goes with them. X is, standard maths for unknown value. So the value that goes with that individual minus the sample mean, and square them all and add them up and divide by n minus 1 and then square root. That's how to figure out a sample standard deviation. And this bit here, that's the variance. The standard deviation was invented first. And then when they were doing their maths about 30 years later, they discovered it was easier to do maths on the variance, like on the thing under the square root, because square roots are just awful. And so they needed a name for this and they called it the variance. So they're really both ways of measuring how spread out things are. The standard deviation has the advantage of being easier to interpret because it's in the same units. See, these are in seconds. And we square them, we end up in seconds squared. And what the hell is a second squared? But when we square root it, we get back to seconds again. And so that's the idea. This is in the same, it's a literal measurement on the x-axis, this standard deviation, but the variance is some other thing. Yeah. Okay. And standard deviations are not all that good on their own. If you have two separate sets of data, you can compare how spread out they are using the variance or the standard deviation, going, oh, this one's got a bigger variance than that one, so therefore this one's more highly spread. But you can't really just look at a random number for a standard deviation and tell whether it's big or small as a standard deviation. That's not useful, but they are useful for comparing two data sets to each other. So just wanted to point that out. People go, well, what does it tell me about the spread? It's like, so it tells me that it's wider than this one because the number's bigger. Yeah. Okay, so that's the thing. I have to first figure out the mean because that's this bit here. They do it with an X bar, don't they? Okay, good. And the mean is what you get when you add them all up and divide by how many there are. And unfortunately, the quickest way is to, if all you've got is a calculator like this, is literally to type them in. Some calculators do have a statistics section, which can do some of these calculations for you. But I wouldn't, I don't know what calculators you're allowed to take into your exam. Graphics calculator. Cool. Well, in that case, we can use the stats version of this calculator. So most calculators have the ability to do some stats, but I would have to remember how to do it. So I've gone to the mode and the stats version. I'm going to do one variable statistics, and it gives me a list that I can type numbers in for my x's. It's a little bit like an Excel sheet with only one column. Now, the thing is that the people who write your exam are aware that not everyone has a calculator that can do this. And so they're actually going to expect you to not do this. They're not writing their exam based on the assumption that you have a calculator that can do this. All right, now I have to figure out how to ask it for the mean. Yeah, this is why you shouldn't do this on the fly. There we go. See, there's a thing on my button here that says stat. I'm gonna... No, that didn't help. Okay. No idea. Sorry, people. I'd have to go look up the book online to see how to do it. So I'm just going to do it the way I was going to. 1.3 plus 2.8 plus 7.6 plus 11.2 plus 1.4 plus 2.1 plus 3.0 plus 2.8. And that is the total. 32.2. So in fact, before I do the mean, I'm just going to say the total like that. And the mean is that divided by how many there are. Oh, I should say n as well. 1, 2, 3, 4, 5, 6, 7, 8. Get my calculator and go that divided by 8. And we've got 4.025. That's telling me that if I took these reaction time seconds and spread them evenly across the 8 people, everyone would have 4.025 seconds. That's what the mean is trying to do. And it is, definitely somewhere in the middle of these. You were guaranteed for the mean to be bigger than the smallest one, which was 1.3, and smaller than the biggest one, which was 11.2. This number is guaranteed to be between the smallest one and the biggest one. So just to check if you're doing it right, if you look at the numbers and go, whoa, this is bigger than the biggest one, you've done your mean wrong somehow. Yeah, it's a good check to begin with. And the quickest way was to just straight up add them up and do the thing. Now, there are 2 ways to calculate the standard deviation. Did I add it up right? Are you showing how to do it on the graphics calculator? Yeah. That's the main problem with calculators. They can do all the things, but you have to find it. So my recommendation is if your calculator can do some of these things, find out how before the exam. That's the big question. Okay, I needed to know the mean. I shall call that X bar. I need to know the mean in order to find the standard deviation. So I've got 2 things I can do. I can either subtract the mean from every one of those and then square those answers and add them up, or there's an alternative way of adding up the squares and doing that as well. But this is the way that the formula that I've got says. Oh, okay. Oh, just bear with me. I've got an idea as well. So I'm going to have to take the mean from all of those. Oh, I don't want to type that 4.025 every time. No, it's just going to be easier. So 1.3 minus 4.025 squared plus 2.8 minus 4.025 squared plus 7.6 minus 4.025 squared plus 11.2. Damn it, need the brackets. 11.2 minus 4.025 squared plus. I'm not going to say them aloud anymore. As much as it freaks me out. Oh no, it won't let me type anymore. I'm gonna have to do the last one separately. Okay. So this thing here was what I get when I add up all of these things. So I can say that the sum of xi minus x bar squared from I equals 1 to 8 is 878.757. But I won't lose it from my calculator. Now I have to divide that by 7 because that's n minus 1 because the n was 8. And now I have to, that's the variance. And now I have to do the square root of that answer. So I did the square root there. And I did the divided by 7 there, just so that you know what I did. And that would be a perfectly legitimate way of showing working, not that you get to show working in your exam, but it's good practice to write it down somewhere so that if you're checking your work later, you can tell if you've done it right. Yeah, I've done 3 decimal places for everything else. I think I've done something wrong. The reason I say that is the standard deviation can't be any more than half the range, and that's that. Damn it! Which 51? Oh, that's an X. Yeah. At some point in that long calculation, I pressed something wrong. I know this answer is wrong. It's way too big, because the range is, yeah. I could be. Yeah, that'll do it. This is not the sort of calculator that can go back more than one step. But it's worth noting that the variance can't be anything bigger than half of the range. But sorry, the standard deviation can't be bigger than half the range. So I have definitely done something wrong, because the range is what, about 10-ish. And so the standard deviation really can't be more than 5. I want to know now. Right, well, let's just do something else. There is an alternative way to do it, which is, let's see if I can find it in the course. Just a second. Okay. In your notes, they just did it like this. The probability of X, like that. And so if you want the mean, which is the expected value, you multiply everything by its matching probability and you add them up. And the concept there is, it's like, well, it's 30% of the time it's 1.3, and 40% of the time it's 2.8, and 30% of the time it's 7.6. And so, well, you include this 30%, and you include this 40%, and you include this 30%, and then that should be the correct answer for the average. Yep. There you go. That's the mean. I'm just going to check something on the computer. Yeah. All right. Just checking something. And the variance is the expected value of X minus the mean, where this is usually called mu, this thing, which is the Greek letter that makes the M sound. So that's M for mean. So what this means is, when you did the expected value of something, you multiplied each answer by its probability and you added them up. When you did the expected value of this thing, you multiplied this thing by its matching probability and add them up. So I'm going to have to go this minus the mean squared times that, and this minus the mean squared times that, and this minus the mean squared times that. That's how to do it. It's just easier for me to write them down as might as well. So I'm going to need that to be 1.3 minus the mean squared times the 0.3, and 2.8 minus the mean squared times 0.4, and 7.6 minus the mean squared times 0.3. And that should be enough to fit in my calculator in one screen and therefore be able to go back and fix it if I did something wrong. Because apparently 6.562, the 3 decimal places. Just let me go back and check if I did it right. Yeah, no, it's not. It's supposed to be a 9. 6.607. That 0.1 is going to make all the difference, people. Okay. And they didn't ask me for the standard deviation, but the standard deviation will be the square root of that, because the variance is the bit before you do the square root. And just as a quick check, if I did do the square root of that answer, it's 2.5. It should be less than half the range. And so my range is about, what, 6.3? Okay, less than half the range. It's not too bad. It can't be that bad. So, yes, it's a nice way of at least checking if you're not horribly wrong. So just as I think the standard deviation of x would be the square root of this. Just to, as a quick check, you can see if it's less than half the range. Okay, we're doing okay. So this is a discrete distribution, this one, because it only has some numbers that it's allowed to be. Well, a continuous distribution can have any number in between all of these as well, and none of them have their own probability. They've all got a height on the graph, but that's not the same thing. The thing is that the variance is the average of how far everything is from the mean. So since it's the average of distance from the mean, you have to figure out distance from the mean and do the average again. Yeah, because the variance is a second average. Yeah, that's why. Like you have to figure out the mean so that you know how far everything is from the mean, and then you have to average that. And that's why we multiply by probabilities, because we're averaging the second time. Yeah. I don't know if that helps. Yeah. Bear with me. When you do the standard deviation, you average twice as well. You do the mean, and then you divide by the n-1 as well. We average twice in this process. We have to average twice in this process as well. This is a population variance. It has to sort of, the sample variance is trying to copy how this works, but just for a sample. And so, yeah, an average happens twice in this story, and it happens twice in this story as well. I have never thought that an average happened twice in that before, so thank you for asking the question. Sometimes you don't notice these things. I've got a chat here. Oh, that's the exact question that someone in the chat asked. Why do we multiply by the px's again? It's because that's the bit where they're doing the average. Correct. Because the idea is that timesing by 30% is saying, well, if you imagine 100 of these, 30 of them would be equal to this. And so we'd have to times this by 30 because this has to be included 30 times. And then later on, we're going to have to divide by 100. But timesing by 30 and dividing by 100 later is the same as timesing by 0.3. Yeah. So, yeah, and we're saying that 30% of the time, the answer is 1.3, which means 30% of the time, you're 1.3 minus 3.79 away from the mean. Yeah, and so you have to include that distance from the mean 30% of the time. Yeah. It's a weird thing to wonder about. the variance. Yeah. No. Because this thing happens a little more often than the others, we have to sort of take that into account. Yeah, this thing happens a little more often, therefore this distance away from the mean happens a little more often. Yeah. Yeah, if they're all 0.3, could totally have just averaged them in the normal way. But I would still do it the long way. Of course, they can't all be 0.3 because that doesn't add up to 100%. And that would not be a valid probability distribution, which is a classic exam question. Here's a probability table. Is this a valid probability distribution? Yes or no? And the answer is yes, because these do add up to 100%. Yeah. Okay, so you've asked why the probability is not showing in the formula. This E here is the bit where the probabilities are. When I did this E, it made me multiply by the probabilities and add them up. And this E made me multiply by these probabilities and add them up. That's what the expected value E does. Whereas this formula, instead of multiplying by the probabilities, I divide by how many options there are, because I assume that all of these are equally likely. So I divide by how many there are. And I adjust it by n-1 because weird ass crap happens when you do square roots. So, and I don't know, it's just, don't get me started on that proof, which I also have to help people to use in other courses. So, yeah. Well done, everyone. You've asked some very good questions so far. We have an hour and we'll deal with some testing. I say to you, if it helps, it's useful to know that every semester people ask me about the hypothesis test, p-values, t-statistics stuff. If that makes you feel like you're not stupid, good, because you aren't. I know you're not, because you've asked some very important and useful questions along the way today. Okay. So someone said that hypothesis testing and rejecting hypotheses sounds counterintuitive, and the truth of it is, yes, it is counterintuitive. It's a proof by contradiction, which is a maths thing, but using probabilities. So you're not always necessarily, yeah, anyway, it's proof by contradiction. So you suppose the thing you don't want is true, and you wonder what it would be like if that was the truth. Yep. Yep. No. Weird. It might have been Nicholas.
Okay, so you're running the session.
Yes, in Harris Slam. Thanks for wading through that. It's been an interesting morning. Okay. Yeah, it's just. It's just, this may be helpful to some people. It's a proof by contradiction. You go, suppose. Wait. Let's just be a bit more precise about that. I want this, and that's the alternative hypothesis. Suppose it's not true. That's the null hypothesis. what would happen then? There's no word that there's no part of this thing that goes with this, but like that's what you're doing. You're going, what would happen then? And you do some calculations and you go, if it wasn't true, the thing I really wanted, this would happen, and yep. You'd get this, that's the test statistic. But that's unlikely. That's the p-value. So I think I do have the thing that I said in the beginning. I know this is very vague. It doesn't work very well if I'm not going to do it with a statistic, actual statistic, and maybe I'll try and do it with a real one. That's the idea. It's a proof by contradiction. It's saying, well, if the thing that I wanted wasn't true, that would be really unlikely, and so this other thing that happened would be really unlikely, and so therefore I don't believe that it's not true, and so therefore I believe that this is true. And so it's like, I don't believe that the thing I want isn't true. It's a double negative. Like you go, I don't believe it's not true, and so therefore it is true. And so, yeah, that's the idea behind it, which is why it's counterintuitive. But when Fisher invented this in 1925, so we're almost at the 100th anniversary of the publication of his hypothesis testing process, it was the only way he could think to do this. Yeah. And it also turned the decision-making process into something that was an algorithm that later people could teach a computer to do. Of course, there weren't computers in 1925, but it was also an algorithm that people could follow using a book of tables and feel confident that they were doing something that was mathematically rigorous. So, yeah. A lot of people just believed Fisher about it. He's a very clever man, rather arrogant, very smug. But, you know, hypothesis testing has been useful over the last 100 years and continues to be useful. Right, there you go. That's how it works. So there are multiple parts to this. This bit's called rejecting the null hypothesis. There's all these pieces here, and sort of all of them have to be described along the way. Yep. And there are little niggly details all along the way. And every time you do this, if you're in a different situation, you have to do it a little bit differently. So different research questions and different data go with a slightly different, the details are different, but the big idea is the same. So for let me just, I didn't know I would have to talk about this today. I mean, I had an inkling that I would, because people always ask. But just bear with me while I think about how I'm going to talk about this. Okay. So at this point, but that's unlikely, it's really how likely is it? And then I decide whether it's unlikely or not. And the only way to figure out how likely anything is to know how likely everything is. The reason you know that when you roll an ordinary die in a board game, that the probability of getting a 1 is 1 in 6 is because there are 5 other options it could have been, and they're all the same probability. And that's true of everything. The only way to know how likely any one thing is to know how likely everything else is too. So to figure out a probability, which is what you've got, and that probability is how you're going to decide whether it's unlikely, you're going to need to know what all the options are and how likely they all are. And that thing of what the options are and how likely they all are is called a distribution. Right. So I'm just going to point that out now. I'm going to need a probability to do this process. And the only way to know one probability is to know all the probabilities. That is what all options are. And what all the options are and how likely they all are. And the name for this thing is a distribution. The word distribution in English means, well, the word distribute in English means to share out. And the word distribution in English means the sharing out of. For example, you can talk about the distribution of a newspaper being where the newspaper goes. And the thing we're talking about where it goes is the probability. How is the probability shared out among all of the options that there are? So that one that we drew earlier, the probabilities were shared out this way. One number got more than the others, but it's not too different. That's what we need to know for our thing. So that's why in this course, like this course was all leading up to hypothesis testing. Like that's where it was going. And the reason they spend all this time telling you about probability distributions is because they're going to be using it to do hypothesis testing. Cool. So some distributions are described with a table. Some distributions are described with a formula. Some distributions are described only with a name, because the name is enough to tell your statistician exactly all the information they need. So you could describe it with a table. Or with a formula that says what the probability is for every individual piece, or with a name. And as far as I know, there are 3 named distributions in this course. Possibly 4. There is the binomial distribution. That sounds familiar, that word, binomial. I'm pretty sure it was in Simon 1. There is the normal distribution, and there is the t distribution. And you only saw the t distribution while you were doing hypothesis testing. It didn't appear any other time. So these 2 appear in the wild. There are things you can do when you measure data that will produce these distributions all by themselves, and they'll just be there already. This distribution only appears when you're doing hypothesis testing. In fact, the t-distribution was invented specially for doing hypothesis testing. Yep. The Z statistic is part of it, is a kind of normal distribution. That is not a stupid question at all. That's an extremely important question. So the Z statistic is the standard normal, it's called. Right. Turns out the binomial distribution looks quite like a normal distribution a lot of the time. And so we can just pretend that it is sometimes. Yeah. It's useful to know the binomial distribution is a discrete distribution. It goes with just single individual numbers. And the normal and t distributions are continuous. So damn it, I think I might color code this next line because I'm starting to put a bit too much information all at once here. This one's continuous, this one's continuous, this one's discrete. That was a bad. Okay. So continuous means that no matter which two numbers you think of, there's always another one between them that's possible. And discrete means that at some point when you get the numbers closer together, there's no number in between them that you can get. In general, discrete things happen when you count how many times something happens, because you can't get 1.5 of something. You just, and continuous things usually happen when you measure stuff. Or calculate averages, because that tends to produce decimal values that you wouldn't have expected when you divide by 7 or something. Yeah. So reaction times tend to be continuous, because theoretically you can have 0.3 of a second. Yeah, but counting me how many times anything happens is discrete. And the only ones you've been told the names of are binomial, normal, and t. And z, but that's a normal distribution as well. This is extremely silly, but you see that I put a cross through a z so you can tell it's not a 2. But if you look at the letter z, you turn it this way, it's an n for normal. That's not why they chose z. They chose z because it was the next available letter after x and y, which had already been used. But anyway, but this works for me. It works for me. The z distribution is the standard normal distribution. They may have chosen z because in German, the word for number is Zahlen, which begins with the letter z. So, not sure. Most of the modern statistics, most of the 100-years-old statistics that we still use today was invented in England. So the German rule might not be any useful. Okay, so the reason why z's and t's appear in hypothesis testing is because, well, t was invented specially for that purpose, and z is the standard normal distribution. And the reason it's called the standard normal distribution, let's just talk about normal distributions. Okay, one more thing. Every distribution has some information to tell you which one it is, because it's not like there's only one t distribution, and it's not like there's only one binomial distribution. There's not like there's only one normal distribution. Binomial distribution occurs when you have a pre-specified number of times you're going to do something, and you count how many times the thing you want happens. So you have trials, and you count the number of successes. Word trial, something familiar? I think they officially call them Bernoulli trials. Bernoulli was a probability theorist back in the day. You count the number of successes and you call it x, and that is a binomial distribution. And the idea is that the number of trials is n. So maybe you do something 10 times, that's the n would be 10. And everything individually, every time you do the trial, it has to have the same chance of happening within that one trial. So I'm just going to add that in here. Sorry, feel free to change your thing, and I'm sorry for making you cross things out. But each trial has the same probability of success within that trial, and that's called P. I say within that trial, but what I mean is it's not the probability that just one out of the 10 will come out to be success. It's saying if you're just looking at that trial, ignoring all the other trials, what's the probability within that trial of getting success? And that probability is P, they call it. And then count number of trials, and you call it X or Y or whatever you want to call it. But it's tradition to call it X. And then you say that X has a binomial distribution with N and P. What I want to say is the binomial distribution is just a little bit different depending on what N and P is. But what you do know for sure is that X could be anything from 1 to all the way up to whatever N is. They're the options that what N could be. You know in advance that N could be any of those things. All of them are possible, but some of them are more likely than others. And the more likely it is in one trial to get a success, the more likely X is to be closer to the N end. And if P is under half, it's more likely for X to be closer to the 0 end. And if P is exactly a half, then it's most likely for X to be exactly in the middle. Yeah, but the thing I wanted to say when I started this, and I got sidetracked by giving you all these details, is that a different N and a different P will change which binomial distribution you've got, because the list of probabilities that go with the different numbers will be different. Different N and P get different distribution of probabilities, right? And so these things, the N and the P, the statisticians call them parameters. You may not have heard this word, but I just wanted to tell you now that's what they're called. Para means follow in Latin. Meter means measure. It's the following measure. That doesn't really help. Okay, so but they are things that tell you about your distribution. They tell you which distribution you've got. So it's kind of like an address. This is very silly, but in my head, city, and in Binomialville, the suburb where the binomial distributions live, that's the address. You go to, you know, street N and house P on that street, and that's the binomial distribution. The normal distribution also has two parameters. It's continuous which means you could theoretically get any number at all. Like literally anything, negative numbers, positive numbers, anything up to billions, every number is possible. But most of the numbers are extremely unlikely. Like so unlikely that you'll just never see them. But they're not. Yeah. So while a normal distribution is a bit like a square, right? In geometry, there's no such thing in real life as an actual square. No squares that you attempt to draw will have all their sides exactly the same length. That's impossible. With a real pencil, that's not possible. But, you know, in our thought lives, squares are things that we understand and believe about. And so normal distributions are like that. There are no times in life where you could measure a human being and theoretically get any number at all. That's not possible. There is definitely some lower limit and some upper limit. But from a probability point of view, it's just easier to pretend there is and let the fact that they're super unlikely just work okay. So anyway, that's some maths philosophy for you. But moving on, any number is possible. But there is one number that is the most likely to be near, and that's the mean. That's the most likely, that's the number it is most likely to be close to. And there's also, it may be that it's really very, very likely to be near the mean and extremely unlikely to be anywhere else. But it may be that it's quite likely to be pretty far from the mean, and that measure of how spread out from the mean you're allowed to be, that's the standard deviation. And we use the Greek letter sigma, which I have never learned to draw so that it looks like something that isn't ridiculous. And the Greek letter mu makes an sound, so for mean, and the Greek letter sigma makes that sound, so it's for standard deviation. And what happens is, when you draw all of the numbers that could be possible, and you draw a nice little curve to say which ones are more likely than which ones. So the most likely thing to happen is the mean. And then this distance here is the standard deviation. From when that curve starts going downwards and starts going outwards. It keeps going down, but stops being like this and starts being like this. It's an inflection point. That's sigma. And so if the sigma is bigger, this is way more spread out, but it has to be lower down because the total area under here is 100%. So, but all normal distributions are the same shape. They're just sort of squished into the middle or taller or shorter or whatever. But it's okay to just draw them like this. And that is so not like, if I drew that and said, hey, these are my probabilities, computer would know that that was not a normal distribution, but close enough. It's just like I can't draw a real square, right? How are we feeling? So these numbers, the mu and the sigma, are called parameters as well. And a different mu and a different sigma would give you different possible numbers that could come out. Because if your mu was 10, it'd be much more likely to be near 10 than anything else. And if your mu was 20, it'd be much more likely to be near 20 than anything else. And if your standard, even if the mu was 10, if the sigma was 5, then it'd be, fairly likely to be, anywhere between 5 and 15. But if the sigma was 2, then it'd be fairly likely to be anything between 12 and 14 and quite unlikely to be further away. The probabilities turn out differently for different mu and sigma. So again, we've got a street, we've got a suburb, Normalville, and in Normalville, we've got all the normal distributions, and on street mu and house sigma, that's where the normal distribution you're looking for is. And there is one normal distribution, which is the best normal distribution. Maybe not the best, but it thinks it's the best. There's the standard normal distribution, which has mu equals 0 and sigma equals 1. And that's the Z. So normally when you do normal distributions, you tend to count in standard deviations. You go, oh, standard deviations, means 20, standard deviations 5. Cool, so I will count in 5s because that's counting in standard deviations. For the standard normal distribution, counting in standard deviations is just counting by 1s. That's why it's the standard. And when you have a number of -1, you're going, cool, that's 1 down. Standard deviation is down from the mean. And that's what that's trying to get at. It measures how many standard deviations from the mean you are is literally just the number you've got. All the other standard deviations, if you want to know, all of the other normal distributions, if you want to know how many standard deviations from the mean you are, you have to divide how far from the mean you are by the standard deviation to get that number. So I'm going, oh, cool. Means 20, standard deviations 5. Here I am at 27. How many standard deviations is that? Okay, 7 divided by 5, 1.4 standard deviations. It's a calculation you have to do. And that's a calculation that's really common. They call it a Z-score because you're converting to standard normal distribution. And the nice thing about normal distributions is that any normal distribution can be converted into Z by subtracting the mean and dividing by the standard deviation. So if you've got X, which is normal, mean mu and standard deviation sigma, then you can go minus the mean and divide by sigma, and you'll magically have a Z. Yay. But the reason you're subtracting the mean is you want to know how far from the mean you are. And the reason you're dividing by sigma is you want to know how many sigmas is that worth. And that's exactly what division is for. It's saying how many of these sigmas fit into this gap. And so it's much less mystical than it looks. So normal distributions are great because every normal distribution looks exactly the same as the Z. It's just more spread out or moved to a different spot. And you can always convert back to Z if you like, which is great. Binomial distributions just don't work that way. They're just different for every N and every P. Sorry, you can't convert one to the other. But if N times P is more than 10, then it looks kind of like a normal distribution, and you just go, yay, we'll just pretend it is. It's great. So the T distribution. Okay, so we had a parameter to tell us the address of our normal distribution. We had parameters, 2 parameters to tell us the address of our binomial distribution. The T distribution has 1 parameter, not 2. It's only got 1. And that parameter is called the degrees of freedom. So your T distribution looks to the naked eye like a normal distribution, but it isn't. It's just a bit different from a normal distribution. But like a normal distribution, like the standard normal distribution, the mean is 0, and that's the most likely thing to get. And like a normal distribution, it comes down on either side, and it's got an inflection point, and it's really unlikely to be anything far away from 0. Once you get past 3, it's just almost impossible to get anything like that. But it's not a normal distribution, it just looks like one. And there's different T's for different degrees of freedom. And so your parameter is called the degrees of freedom. So there's only one street in T-Town. You just have to go to the right house. Actually, in my head, the T's live in an apartment tower, the T towers, and you press the number on the lift and you go to the correct floor. And just so you know, the infinitieth floor is the Z distribution, like Lord Business in the Lego movie. Yeah. So if you have an infinity degrees of freedom, then you get Z, which is kind of mysterious, but there you go. So that's the degrees of freedom. Now, degrees of freedom is a weird ass thing. What the hell does that even mean? There are reasons why it's called that, but essentially it's to do with the fact that there's an n-1 in this formula just here. And it's saying that basically, if you know what the mean is, if I told you the mean of something was 3.79, and I said there were 8 numbers and their mean is 3.79, you could know 7 of them. And then if you knew what the mean was, then you'd have to make the last one a certain number. You wouldn't have any choice about that one if you knew the mean had to work out to 3.79. And so that's the ones, if you know what the mean is, you've only got freedom to change all but one of them, because then the other one is whatever it is to make the mean, whatever the mean has to be. And that's why it's called degrees of freedom, as far as I know. Could be making that up, but it works. But for me, in my head, degrees of freedom has this abbreviation, which is just the same distribution abbreviation as distribution finder. It finds the correct T distribution. Yep. And it turns out, actually it's the other way around, but anyway, it turns out that when you take a sample mean and divide by the and take off the real mean and divide by the sample standard deviation on square root of n, then what you get is a t distribution. Which is, you know, and that seems mystical, but it's actually not, because this is the calculation you would do to find a z. And then when Gossett in like 1910-ish went, when I do the calculation on this, it doesn't actually turn out to be a normal distribution. What distribution is it? And he figured out what distribution it was and went, I shall call this, well, actually he called it Z, but Z had already been taken. So they later called it T. Later on, people called it the T distribution. There you go. Don't know why T. Maybe we'd already use X, Y, and Z. Yeah, T, I suppose, is the next available letter. I could have used U or V or W, but apparently we don't want to use those. Okay, maybe it's T for test statistic. That makes sense. Okay, how are we feeling about all that? All right. So this was literally invented because of the calculation you do to do test statistics. And they went, not normal, what is it? And it's the t distribution. And you get a different one for every whatever. And the reason you only need one thing to tell you which one it is because you've already gotten rid of the mean and the standard deviation by subtracting it and dividing by it. That'll always produce this 0 and 1 thing. And so it's the n that makes the difference. That's why. This n is not an n minus 1, by the way. The n minus 1 is part of the s. Yeah. Okay. While I'm at it, distributions is a big idea in statistics. Theoretically, anything that you could measure or write down or calculate has a distribution. You might not know what it is, but theoretically, somewhere in the fabric of the universe is a description of the probabilities of everything. So if you measured, 8 reaction times and calculated their mean, well, every time you measured 8 reaction times and calculated their mean, you would get a different answer. And those different answers would be more or less likely than other different answers. And so the mean of 8 people's reaction times, that thing that you're imagining calculating and measuring and calculating multiple different times, that thing has a distribution too. There should be, theoretically, a list of all the possibilities that are possible and how likely they all are. And that's always true. Well, we imagine it's true. This is the philosophy of statistics. Everything has a distribution. And so when you collect data and you measure a number on multiple different individuals or multiple different times, and then you do the average, the averages, those means of the group could have been different with different groups. And so that number has a distribution as well. And that's called a sampling distribution. So when your lecturers talk about the sampling distribution of the mean, that's what they're talking about. They're saying, well, what are all the means and how likely are all of them? And so it will be a different distribution for what it would be for an individual person. Yeah. So just as an aside. So for an individual person, you might have a reaction time of like 3 seconds. And it ranges from 0 seconds, probably not all the way down to 0, but 6 seconds, something like that. And maybe it has a mean of 3 and a standard deviation of 1.2 or something ridiculous. Just making up crap. But for 8 people, And every one of them has a number of their own for their reaction time, but the group of them has a mean reaction time, and that's a number. And different groups of 8 people would have different means, and those things also have a distribution. And the mean will still be 3. If every individual person has an average of 3, then when you average 8 people and do all the average of all possible groups of 8 people, the average of those averages is also 3. But the standard deviation will be lower. A group of 8 people, their mean will be closer to another group of 8 people's mean than 2 individual people's numbers will be. Because you've sort of averaged out the variation. So groups are closer to each other than individuals are, basically. And so the standard deviation is still 3. The mean was still 3. The standard deviation is 3 on root 8. That is the law, mathematical law. And the really cool thing is that even if this isn't normal, if this n is big enough, this is normal. Well, approximately. It's just really cool. It's called the central limit theorem. It's so important it's called a theorem. It's like the only one in stats. Yeah. So, but even that's great. I can now go all the way back to the beginning. Wait. Yeah. See back here. Back here. What would happen then? All of this distribution stuff is about the what would happen then. What if the mean really was 3? What would happen then in my sample? And I'm starting to think here about the what would happen then in my sample. Going, cool, this is what would happen in my individual person. This is what would happen in my sample of 8 people. And that's lovely. But what if that's great? But it'd be really nice to just have a standard way of doing this instead of having a different distribution for every possible situation. And so what your Gossett did is he went, and his friends before him, they went, cool, we'll just take off the mean and divide by the standard deviation, and then it'll be standardized. You know, minus mu divided by that sigma on root n, and now it's 0 and 1. Now it's a standard normal distribution. Yay! And so instead of messing around with this crap, we'll just do standard normal distributions. So it is theoretically possible in any situation to calculate a nice thing that you can calculate that will have a neat little distribution that's easy to look up. That's the goal of a lot of statistical tests. In this course, all you've got is Z's and T's. You go, cool, neat little distribution. Oh, I've said 4 twice now. That would be a 6. All you've got is Z's and T's. But there are some other distributions that people have invented over the last 100 years, and you might meet them if you do more statistics. You know, econometrics, for example, is just more statistics. So you've already seen one. If you look closely at your regression output, there'll be an F, and that is a distribution too. And it has 2 parameters, which are both called degrees of freedom, just to make it interesting. And it's called F after Fisher, who invented it, because, you know, he was that sort of arrogant person. So, yeah, and there's a chi-squared, and there's W's, and, you know, there's lots of fun ones. But the classic ones of your Z and your T, if someone can make it work out with a Z or a T, then they'll try. And so it turns out when you do regression, you get t's as well, but you calculate them slightly differently. But what they've done is they've deliberately set up the calculation so that it does turn out to be a t, because they've already got a list of t possibilities that they can look up. Yeah. All right. Wow. I'm going to have a small thought break, and I will go to the last 10 minutes. How are we feeling? We've got the vibe.
So basically, we're just trying to make it into a model and figure out from that.
Mm-hmm.
The reason for the key type of specific.
Yep. Degrees of freedom tells you which specific distribution to look up your probability in. So what you need to know is which situation is Z the best one for, and which situation is T the best one for. And Z doesn't need parameters because you know what they are. They're automatically 0 and 1. But the T does need a degrees of freedom to tell you which one. Yep. If n is more than 30, you can use Z. To be fair, if you're using Excel, even if n is more than 30, it will still use T anyway, because it's a computer. It can be as accurate as you need. But the central limit theorem says that basically says that a T distribution is pretty much almost a normal distribution. You know how I said that the T distribution with infinity degrees of freedom is a Z? Well, for most purposes, 30 might as well be infinity. Right, from a statistician's point of view. I remember talking to one of my statistician friends and they're going, oh, well, in statistics, there's sort of like the numbers 1 to 10 and then like infinity. So, yeah. At least for degrees of freedom. But, so that says to me that they might give you some probabilities that go in the exam in a table, maybe give you the probabilities that go with T up to like 30. And then after that, you just use Z. Yeah, because they can't guarantee you'll have a calculator that knows how to do T probability calculations. So they're going to have to give you a table of some sort. Did they say they'd give you a T table? Yeah. So just so you know, the infinity row of the T table, which is the last row, is the Z row. And that's a really useful thing to know. Okay. So last 10 minutes, how do you tell which one is which? So do you get to take notes into your exam? One-sided? Yep, cool. I've said this so many times. I don't know why your lecturers made work for themselves by making it one-sided. They're going to have to check now. And just, yeah. I don't see why one-sided when they could just not check and give you two-sided and everyone would feel better and they would have less work to do. But, you know, this is the universe we currently live in. So that process of hypothesis testing, how do you make the decisions of all individual bits? Now, I can't do it all in 10 minutes, but I can talk about some details. So, for example, wait, just a second. I have to think of one. Manufacturer of cake mixes. Like Sarah Lee. So they're going to sadness. They're going into administration after 50 years of providing the world with cake mixes. Anyway, manufacture of cake mixes. Less than 5% of. Oh, I'm going to speak a different number than 5 just to make it easier to distinguish from other things. Let's say 3%. To fail, to rise when cooked. They trial 100 mixes. and 5 fail to rise. Wait. I'm gonna do 1,000. Thank you for bearing with me. $42 fail to rise. Is this enough evidence to conclude a more than 3% fail rate? This is a classic exam style question. I don't know if they'll give you one of this complexity. They may do one and do part of it for you and ask you to do the last bit or the first bit or whatever. Okay. So we're trying to make a conclusion. That's what hypothesis tests are for. And my conclusion will be based on statistics calculations, because this is a statistics course. And so, or because, you know, statistics is fairly convincing to people, so it's a good thing to use. Let's think about the individual objects that are under study here. We have cake mixes. And each individual cake mix, only 2 things can happen. It either rises or it fails to rise. I haven't measured any numbers on each individual object. All I have written down is whether an event happens or not. That's really important. The fact that there's only individual numbers means that individual yeses and nos means that I can't do an average of those things. All I can do is calculate a percentage. Which means that I'm wondering about a percentage, which in statistics is a proportion. So all of this goes through my head in about 10 seconds. Right, proportions, cool. I have a question, a yes or no question about proportions, and I'm wanting to conclude that the proportion is more than 3% or not. Let P be the true proportion of all cake mixes that do fail. And my alternative hypothesis, which they've already told me, is that I would really like to conclude that this is more than 3%. Actually, I really don't want to conclude that. That would be sad. But that's what this sentence is. Can I make the conclusion that it's more than 3%? So that's my alternative hypothesis. The conclusion that the proportion is more than 3%. How do you feel about my decision-making process there? Cool. I'm really sorry that your course has one-sided hypothesis tests. It can sometimes be one word that makes all the difference as to whether it's a greater than or an equal. I'm sorry. Hopefully they'll be nice to you and make it really obvious. Some statistics courses don't have one-sided ones. They only have not equal. Sorry, I feel sorry for you. But those other courses compensate for that by just having more hypothesis tests to do. So, you know, swings and roundabouts. And the alternative hypothesis, the null hypothesis, is always equal. And the reason for that is, you would think that the opposite of being greater than 0.03 would be being less than 0.03. But I can't do maths if the P is lots of different options. I can only do maths if there's only one option for what the P could be. And so your null hypothesis has to be a land where there is only one option for what the P could be. And so that is why the null hypothesis always equals. because you have to pick a universe that you're imagining. This one. What if this big what if question here? Where is it? This big what if, what would happen then? This suppose it's not true. We have to do calculations in that supposal, and we can't do calculations unless we have a specific number for this. So that's why it's equals. There you go. Cool. Now I've been really fun because this one says less than 3%, this one says more than. I've specifically chosen the one that goes with the conclusion that they've asked me about. That's why I chose this one. Okay, so here we go. That's the beginning. Choose your null hypothesis and your alternative hypothesis. And usually you think about the alternative first and then choose the null to be the equals that is right on the edge of that. And then we have to choose a test statistic. Now let's imagine. This is my imagine. This is what's going on in my head. Here's my cake mix. It either rises or fails to rise, but I'm going to say fails to rise, yes or no. And then when I have my 1,000 cake mixes, then each one of them fails to rise or doesn't fail to rise, and I can write down how many fail to rise. And that is any number from 0 to like 1,000. And that's a binomial distribution, because each individual thing, you've counted how many times something happens. That's what a binomial distribution is. And in the land of the null hypothesis, they all have the same probability of failing. It's 3%. But I don't want to calculate normal distributions, and I want to convert it into something that I can look up. And so that number of the number that fail to rise, so this is all going on in my head at the moment. That number of the number that fail to rise, I can take off its mean and divide by its standard deviation and produce a normal distribution. Because it will be approximately normal, because that's how binomial distributions work. So my test statistic is a Z, which will be, fuck, sorry. That's the raw number. The p hat is the sample proportion, which is the number you have out of the 1,000 in our case. So in our case, the p hat is 0.042, because it was 42 out of 1,000, right? Which is 4.2%. So anytime there's a hat on something, it means this is the estimate from my sample, just so you know. Happens later when there's a y hat in regression as well. I still don't know why the sample mean isn't called mu hat. Don't know why. Sorry. And so the test statistic is to turn this calculation that we've got here into something that we know how to deal with, and it will be a Z, which is the p hat minus the p from the null distribution divided by that, I believe. Pretty sure that's right. Do they use the Q in this course? So Q stands for the other percentage. We've got a 3% for our P, and so our Q will be 97%. So in our case, that'll be 0.042 minus 0.03 divided by the square root of 0.03 times 0.97 over 1,000. So whatever that works out to be, that's my Z statistic. And the reason you're choosing this Z statistic is that it should have a standard normal distribution if you do this calculation, which is much easier than messing around with binomial distributions. That's the idea behind it. So I'll need brackets around this top line because it's held together by the bar on my page, but the calculator can't see that bar, so I'm going to have to put in the brackets myself. The square root. The square root will hold together all of this by itself. .223. Okay. So this was the bit where I calculated what happened. This is the what happens now bit. But I need to know all the things that could have happened. Officially, it's only standard normal if P times N and Q times N are both more than 10. So I probably should check that. So let's see, we got 42 failed to rise and 97 rose. Both of those numbers are more than 10. We should be good to use a normal distribution. Not even 97. 42 and 968. No, for 58. Both greater than 10. So it's okay to use a normal distribution. If you don't have that situation, then you have to use straight up binomial distribution on the original data, which is just harder. Yeah. So the number that happen and the number that don't happen both have to be more than 10, basically. Or is it? Yeah, if 42 was 9, then we wouldn't be allowed to use a normal distribution. But actually, just a second. It's not your data, it's the null hypothesis, actually. You've got to use the null hypothesis percentages. So even if the 42 was a 9, because we're comparing to 3%, whose number would be 30 out of 1,000, that would be okay. So if we were comparing to only 1%, would be right on the edge of being okay. Yeah. Okay. And if our sample size was only 100, then we'd only have 3 in that spot, and it wouldn't be okay to use the normal distribution. That's why I chose 1,000, just to make it work. So it's got to be the number that you would have expected out of the sample. So this is the 0.03 times 1,000 there, and this is the rest of them. Okay, so we imagine all of the z's that could have happened, and they have a 0 in the middle, and 1, 2, and we're about here. That's the z that we actually got here. Yeah, a lecture is recording in here. I've just paused the recording so they don't get our statistics on there. So these are all the things that could have happened, and this is the one that did happen. The 2.223. And so I need to imagine how unlikely would it be to get 2.223? It's quite far out into the edge. It's more than 2 out. It's pretty unlikely. And the way that we calculate the probability is to figure out the area that's beyond. Yeah. If it was two-sided, I'd figure out this area down here as well. And that would be you'd get it from a computer or from something. Or compare it to the standard, to the critical value you would have expected. Did they talk about rejection region things? Yeah. So for standard normal, okay, just a second. We haven't decided what counts as a low probability. If this probability works out to like 10%, is that low? Does that make us conclude? Is that enough evidence to conclude that the proportion is more than 3%? I don't know. You have to make a decision. And that decision is called alpha, usually. It's called the significance level. And most people say to use a 5% significance level. That is tradition. But you can be told to use any level, but if nobody tells you, then you use 5% because that's what Fisher used when he invented this in 1925. And so standard rejection, damn it, we'll use a 5% level. And so when someone says level of significance, I mean, that's the cutoff for when a p-value counts as low. So if your probability, now this p is not the 3% that we're talking about, that's the proportion. I'm talking about the p-value that we're about to figure out, this black area here. If that p-value is low, and by low we mean under the significance level, then that will conclude as strong evidence. And if we figured out what the Z would be that went with that, then if our Z was further out than that, then the probability would be less than 5% because it's further out and therefore more unlikely. So for a standard normal rejection region with 5% significance, one-sided, the critical value is 1.645, I think. I'd have to look that one up, but I'm pretty sure that's what it is. Most people, if you see the 5%, think 1.96, but that's the two-sided one, and we've only got one side. And so the calculated is more than 1.645, and so therefore we reject the null hypothesis and conclude that P is in fact more than 0.03, because that was the alternative that went with it. So this bit here, where I had my Z that I calculated being further out than the Z that would go with 5%, that's the bit where I decided that what happened today was unlikely. And therefore I don't believe that's my contradiction in my proof by contradiction. And so when I suppose that the proportion really was 0.03, and I eventually got to saying that's unlikely, not 0.03. So I conclude it's more than 0.03. And in fact, it's closer to 40% than it is to 30% based on my data. So is this enough evidence to conclude? You'd say, yes, this is enough evidence at the 5% significance level. It's really important to keep in mind which percentage goes with what part of the story. This percentage is the p-value. This percentage is the proportion. They're different. This is part of the original story about my manufacturer, whereas the p-value is always there, no matter what. So you've been taught one for proportions like this. You've been taught one for a mean, a single mean. And you've been taught two for a single mean. So is the mean this number? That sort of research question goes with, and there's two situations that go with that. We know the true sigma, and then in that case, we'll use a Z, and that'll be that. But if you don't know sigma, which means, and when I say sigma, I mean the population standard deviation. If you don't know sigma, which means you use the sample standard deviation, that means you use a t instead. But it looks very similar. It looks almost identical, except this is a sample standard deviation in this spot, as opposed to the population standard deviation. That's the difference. And theoretically, if you're using a sample standard deviation, you are supposed to use a t no matter what. But if n is more than 30, then the t distribution is almost identical to a normal distribution anyway. And so it works out fine to use a z anyway. That's the idea behind it. Because the closer your t gets to, yeah. So that's how it works. And is the proportion this number? We've just done that. We use z. Yeah, that. And is this mean equal to this mean? And that uses a t. And again, there's a know the true standard deviations and a don't know the true standard deviations version of that. In past versions of this course, you've had a can you assume that standard deviations are equal and a can you assume the standard deviations aren't equal version of that as well. Of course. That would be too easy. But all of them use a t, just a different calculation for t and a different standard deviation. I'm just going to go next page and do it on there. And so you'll know that means like you've got mu1 equals mu2, something like that. It's your null hypothesis. And so this story is usually like they give you two distinct situations and say, well, we think the mean in this, measure the mean in both. So I'm pretty sure, could be wrong, but there is a, is standard deviations equal, or the variance is equal, and there is a standard deviations not equal. I was always taught that if your sample standard deviations are no more than the biggest one isn't more than twice the smallest one, then you'll be good to use this one, but I don't know what's in this course. So, yeah. So like if you had a standard deviation of 10 in one and a 15 in the other, then it would only be bad if 10 in one and 22 in the other. Like if one of them's more than twice the other one, then it's bad, but we would have to look that up. Yeah. And I can't remember these ones off the top of my head, which is why we have cheat sheets. Look them up, but they all look something like this. They'll have like a and like an x1 bar minus x2 bar over something with a square root under it, and you'll have a t like that. And you have a different decision rule as to what the degrees of freedom is as well in each situation. But go look it up. Again, as I said, different courses have slightly different rules for how you calculate these things. So just look it up inside your My Uni to see what your lecturers say. Yeah, don't just Google it. You may get something a little different to what your lecturers say, especially with the degrees of freedom for the standard deviations not equal case. So, yeah. And so, as I said, there's all these little niggly details that you have to keep track of, but the big idea is the same. You always have a null hypothesis and alternative hypothesis at the beginning. You always calculate something, usually a Z or a T in this course, and then you look up the probability that goes with it. And based on the p-value, if that's low enough, you reject the null hypothesis. And if it's not low enough, you say, there is not enough evidence to reject the null hypothesis. So I prefer p-values. They make sense in my head. And rejection regions are just the region of Zs that would make the p-value low enough. That's what it is. And so just so that we've got that right in our heads. That's the p-value there. That will possibly both sides if it was two-sided. If you knew that this Z was exactly 0.05 for the p-value, then anything that's further out has got to be less than 0.05, and anything that's further in has got to be more than 0.05. That's the idea behind it. And so this is called a rejection region here. Because any number in that zone is guaranteed to be less than the 0.05 because you're further out, so you're taking up less of the area. Yeah. Interestingly, the 0.05 was chosen specially so that the rejection region for your standard Z is about 2 for a two-sided one. This is 1.96. And so when Fisher invented this, he invented it based on rejection regions because he went, well, if I was teaching my biologist, my agriculturalist to do this, when they got their Z and they saw it was more than 2, they'd go, cool, I reject. And he thought that 2 was a nice number. And so he figured out that that went with about 5%. And so he worked backwards and went, the p-value is 5% that goes with the cutoff. I only learned that this year. So I keep repeating it to try and help remember it. Yeah, so personally, I find rejection regions confusing. I prefer to talk about p-values. And even if I don't calculate the correct p-value, I would just make reasoning and say, well, if Z was 1.645, the p-value would have been 5%, 0.05. My Z is greater than that, so my p-value is less than 0.05. And actually, I prefer to reason it out that way. Yeah. But from an exam point of view, this is the easier one to do in an exam if you don't have a calculator that can actually calculate the probability. And so I reckon that they'll give you some critical values of Zs and Ts that you can compare to based on what you've got. It is time to stop. Gone good, nearly half an hour over what I said I would, but I wanted to round that out before I finished. I hope that was okay. Okay, I will stop the recording there.